So this is our second video in the energy stores, work, power and efficiency tutorials. In our previous video we had a look at how we calculate the energy in kinetic stores, gravitational stores and elastic potential stores, and we looked at describing the changes in stores of energy when there are changes in a system. In this video we're going to look at how we calculate the work done in three different ways: mechanically by force, by a current in an electrical circuit, and by heating. It may be that you're watching this video to introduce one of these topics, in which case you might not be ready to look at all three methods of calculating work done, or it might be that you are watching this video as revision. You've already learnt about all of these different three types of work done, and so you're using it as an overview. Whichever one you're doing, press the pause button when needed, write summary notes, bring questions to the lesson. We're also going to look at calculating the power and efficiency in different situations where work has been done, and we are going to look at ways to improve the efficiency of different systems. So remember, write your summary notes, bring any questions to the lesson, and remember to use the pause button. So as a brief recap from the previous video, just in case you haven't seen it, in the previous video, one of the most important things we said was we reminded ourselves that energy cannot be created or destroyed. It can only be transferred into a different store, stored or dissipated and wasted in the surroundings. We looked at the different stores of energy that we see at GCSE Physics. So we looked at calculating how much energy was in a kinetic store, a gravitational store, and an elastic potential store. We also reminded ourselves about the thermal or internal store of energy, using either term is fine at GCSE. We looked at chemical stores of energy, the stores of energy that you get in a battery or in your muscles or in food. We looked at the nuclear store of energy, which is the energy stored inside the nucleus of an atom that might be released through radioactive decay, fission or fusion. And then we looked at the electrostatic stores of energy and magnetic stores of energy. And we said that these might also be known depending on whether you're doing GCSE, A-level or IB, which exam board you're doing for, etc. For example, that this might be known as the electromagnetic store of energy, but either terminology at this point is fine. So these were our different energy stores that we could see in different systems. And we had a practice at describing the changes in the stores for different situations. And we then said, well, if we're going to transfer energy from one store to another store, we have to do work. And that term in physics has got a very specific meaning. It means we're transferring energy from one store to another. So we looked at different ways that we could do work. And we said that we could do work mechanically by force. Forces do work. They transfer energy from one store to another. We said that we could transfer energy or do work by a current flowing in a circuit, by charges flowing. And we also said that we could do work by heating. So those are our different ways of doing work. And what we're going to look at now is how we can calculate the amount of work done via these different methods. So here we are, our three different methods of doing work: forces, heating and a charge flowing. Let's remind ourselves of the equations for work done in these different situations. So if a force is transferring energy, if a force is doing work, we have this equation: the work done is equal to the force times the distance moved in the line of action of the force. Remember, this equation is not given, so we need to remember this and memorise it so that we can recall it in an assessment situation. If we're looking at work being done by heating, so we have got two possible equations that we might use. We could use the change in energy. Remember, this triangle here is the mathematical symbol delta, so it means the change in. So this equation reads as the change in energy is equal to the mass times the specific heat capacity times the delta symbol again, so the change in temperature. So that's one equation. There's also another equation. This one is for when there's a change in temperature, but you could also get a change in state, and then we'd use this equation here. So this is the energy is equal to the mass times the specific latent heat. This one is given, so you just have to remember to go and look for it on the equation sheet. And then finally, if we've got a charge flowing, in a circuit, we could calculate the work done because the energy is equal to the charge times the voltage. This one is not given and needs remembering. So a couple of little things to note about these equations just to make sure we don't get caught out. Here, W stands for work, which is measured in joules. S is the distance moved along the line of action of the force, and we can use this equation to define a joule as 1 Newton meter, and we need to be able to convert between the two. So 1 joule is equal to 1 Newton meter. If we have a look now at some of the nuances of the heating work equations, if you've had a look at the thermal topic in the physics GCSE already, you should hopefully be familiar with the idea that the energy in the internal store for an object is a combination of the kinetic energy of the particles in that object and the potential energy of the particles in the object. The kinetic energy of the particles links to the temperature of the object, and the potential energy of the particles links to the state of the object, whether it's a solid, a liquid or a gas. So depending on the situation, if we've got a situation involving a temperature change, we're going to be changing this aspect of the internal energy store. And if we've got a change of state, so maybe it went from a solid to a liquid or a liquid to a gas or vice versa, then we've got a change in the potential energy here. And we're going to use different equations. So this equation here, the specific heat capacity equation, that's going to go for a temperature change because look, here's the temperature change in the equation. But this one here, we'll remember that when we've got a change of state, there is no temperature change. And so you have to use this equation here, which doesn't have that change in temperature part to the equation. Just remember that mass needs to be in kilograms. Delta means changing, it's just a mathematical symbol. C is the specific heat capacity and L is the specific latent heat. And then finally, if we're looking at the equations for work done when a charge is flowing, Q is the charge, which is measured in coulombs, capital C, and V is the potential difference measured in volts, capital V. So let's do some worked examples now, calculating work in those 3 different types of situation. So let's revisit the slide example where a child is going down a slide that we saw in the previous video. We have a child of mass 45 kilograms going down the slide, and it's in this question we're going to say that at the bottom of the slide the child is travelling at a velocity of 5 meters per second at the bottom of the slide. Calculate the work done by friction and the size of the frictional force. You can see from the diagram the slide is 4 meters high and the child is going to travel 8 meters along the slide here. So first thing we need to do, write down our knowns and unknowns. So here we go. The mass is 45 kilograms. Those units are fine, they don't need changing. The height is 4 meters. The distance travelled in the line of action of friction is going to be 8 meters. The velocity is 5 meters per second. We want to know the work done and we want to know the frictional force. Next, we have to think about what equations we're going to need for this situation. So we need to recall our equations for the work done by frictional forces, because this is a mechanical example. We need to recall the equation for the energy in a gravitational store and the energy in a kinetic store. And here we go. Here's our equation for the energy in a gravitational store. Here's the equation for the energy in a kinetic store. And here is the equation for mechanical work done. Work equals force times distance in the line of action of the force. So in terms of what we're trying to do here in interpreting the situation, the child at the top of the slide has got a store of gravitational energy. As the child goes down the slide, the energy transfers from the gravitational store into the kinetic store as the child is moving. Now, in this case, not all of the energy that was in the gravitational store is going to go into the kinetic store. Some of it is going to be transferred via friction. Work is going to be done by the force of friction, and it will go into the thermal store of the slide or the child. So let's have a look at putting some numbers in and work out how much energy we're looking at in these different stores. So here we're going to work out the energy in the gravitational store, So the mass is equal to 45 kilograms. So we're using mgh from down here. G is going to be given to us. It is 9.8 meters per second squared, acceleration due to gravity on Earth. And the height is 4 meters. When we do that, we find that the energy in the gravitational store is 1,764 newtons. 64 joules. So that's how much energy was in the gravitational store at the top of the slide. Next, let's work out how much energy was in the kinetic store at the bottom of the slide when the child was travelling at 5 meters per second. So here we are. We're now calculating the energy in the kinetic store using the kinetic energy is equal to half mv squared. Don't forget the squared. So we've got the energy in the kinetic store is equal to half times 45 kilograms times 5 squared. And if we put that into a calculator, we should get that the energy in the kinetic store is equal to 562.5 joules. Now you can see that these two are not the same, but we know that energy cannot be created or destroyed. So this missing energy that hasn't gone from the gravitational store into the kinetic store must have been the energy transferred by friction into the thermal store. So next job, work out how much energy that was. So here we go. I've done 1,764 joules minus 562.5 joules, and that gives me 1,201.5 joules. So this is the work done by friction, the energy transferred by the force of friction to the thermal stores. Now that's the first part of the question here. The second part said the size of the frictional force. So if I have a look at this equation here, work is equal to the force times the distance moved in the line of action of the force. We know the distance moved in the line of action of the force. Friction acted for 8 meters down this slide. So let's try and work out the size of the frictional force. So I'm using work is equal to force times distance. I rearrange that to say force is equal to work divided by distance. And that gives me 1,201.5 joules divided by 8 meters, which gives me 150 newtons. So in this example here, the frictional force was 150 newtons acting between the child and the slide. Okay, so that was our first work calculation, looking at mechanical work done by forces. Next, we're going to look at a situation where work has been done via heating. So in this example, a kettle is filled up with tap water at 12 degrees C, and it brings 0.5 litres of water to the boil. How much energy must the kettle transfer to the water in its thermal store to do this? Water has a specific heat capacity of 4,200 joules per kilogram degree C. So first thing we need to do, write down the knowns and the unknowns. Here we go. So we've got a specific heat capacity, 4,200. We've got the change in temperature in this situation. We know that the water was made to boil, so that's 100 degrees C, but it started at 12 degrees C. So we've got 100 minus 12 gives us 88 degrees C as our change in temperature. The mass of the water is 0.5 kilograms. I won't go into a huge amount of detail here on how this is done. There are other videos that will explain this in terms of the density of water. But essentially, something that's always useful to remember is that 1 milliliter of water is has a mass of 1 gram, but that's only for water because of its density. So if we've got 0.5 litres of water, we have got 0.5 kilos of water. And then this is our equation here that we're going to use, our specific heat capacity equation. The change in energy, delta E, is equal to the mass times the specific heat capacity times the change in temperature. Let's put some of those numbers in. So here we go, the change in energy is equal to 0.5 multiplied by 4,200, that's the specific heat capacity, multiplied by the change in temperature, 88 degrees. When we put those numbers in, we get 184,800 joules. Now might be a good time to just remind ourselves of our use of prefixes. I could also write that as 184.8 kilojoules. So if we've got the prefix capital K here, kilo, that's 10 to the power of 3. Or I could write that as 0.18 megajoules. If you've got a capital M prefix, that is 10 to the power of 6. So let's have a look at this situation now. We're going to try and work out the work done by a charge flowing in a circuit, and we're going to stay with the previous example, this kettle boiling water. So the kettle that boiled the water was plugged into the UK main supply. What do we know about the UK main supply from our electricity topic? Try and trawl through the memory banks. And it took 80 seconds to boil the water when a current of 11.5 amps was flowing. Calculate the work done by the current. First thing we need to do, write down unknowns and unknowns. So the time is equal to 80 seconds. The current is equal to 11.5 amps. The voltage is equal to 230 volts. We need to find out the work done by this kettle, by the circuit in the kettle. And here are our equations that we're going to need to use. The energy is equal to the charge times the voltage, and the charge is equal to the current times the time. So let's have a little look at putting some of those numbers in. So let's find the charge. It's equal to the current times the time. So we've got 11.5 amps multiplied by 80 seconds. So that gives us a charge of 920 coulombs flowing while the kettle is boiling the water. If we now use that charge to find the work done, the energy transferred, I've got E equals QV. Energy is equal to the charge times the voltage. So I've got 920 coulombs multiplied by 230 volts from the UK main supply. And that gives me a work done of 211,600 joules. And again, if we practice our prefixes, that would give me 211.6 kilojoules, 10 to the 3, or 0.21 megajoules of work being done in this circuit. So that's us having a look at calculating the work done. And now we need to remind ourselves of power, what power is in terms of a concept in physics, and how we calculate it. We've got two possible ways to remember this power equation. But essentially power is equal to the work done, or the energy transferred, it doesn't matter which one of these you use because they're equivalent, divided by the time. So anything that transfers energy in a certain amount of time will have a power. The quicker it transfers that energy, so the smaller the time, the bigger the power will be. And that works as a fraction. If this number gets smaller in this equation, this number here is going to get bigger. A couple of things to remember about the equation. Power is measured in watts, which is going to be represented by a capital W. Don't confuse that with the symbol for work done, capital W, that you get in the equations. Time is going to be measured in seconds in this equation, and the work done is going to be measured in joules. Now, if you're looking at power in electrical circuits, there's another equation that you can use, which is that power is equal to the current times the voltage. PIV is a good way to remember it, okay? So for electrical circuits, this equation might also be useful. Power is equal to the current times the voltage. And remember that from these equations up here, we're going to say we can define the watt. So 1 watt is when 1 joule of energy is transferred in 1 second. So if we go back now and revisit the example with the kettle boiling the water, we can work out the power of the kettle. So the kettle transferred 211,600 joules in 80 seconds. So that gives us, if we do the work divided by the time, we get 2,645 watts. Now we could also try out that other equation that we saw, P is equal to IV, and see if we get the same answer. So the power of an electrical circuit is equal to the current times the voltage. 11.5 amps multiplied by 230 volts, we get 2,645 watts. So, we get the same answer. That is all great. Now that we've had a look at calculating the work done and the power, the final thing we need to look at calculating is the efficiency of an energy transfer. So let's have a little look at this topic of efficiency. What you can see here is a Sankey diagram. This is a scale diagram. Along here, this width of the arrow represents 100% of the energy, and then as the transfer happens here and some of the energy is transferred from one store to another, you can see that the arrow gets thinner, and the widths of these arrows represents the amount of the proportion of the energy transferred. So this is called a Sankey diagram, okay, and it's drawn to scale. Now, in this diagram, this is a diagram for the kettle. So you might remember that in the previous examples that we were doing, the energy that was transferred by the circuit to the kettle was larger than the energy transferred to the water. So some of the energy was being transferred somewhere else. And this Sankey diagram is representing that energy transfer. So at the beginning we had 100% of our energy, and 87% of that energy is transferred to the thermal store of the water by heating. And this is useful. This is what we want the kettle to do. We want the kettle to transfer energy to the thermal store of the water. So this is the useful energy stored. But down here, some of the energy was transferred to the thermal store of the kettle and the surroundings. So the kettle increased in temperature and the surroundings around the kettle increased in temperature because of this wasted energy that was transferred to it. That wasn't useful, so we refer to this as wasted energy. So 13% of the total energy we had at the beginning has actually dissipated and has been wasted into the thermal store of the surroundings. Now, as well as representing this transfer of energy via a Sankey diagram that's drawn to scale, I can also calculate it with this equation. So here we go. Efficiency is equal to the useful output of the transfer divided by the total input. You could, if you wanted to, multiply your answer by 100% to get your efficiency in a percentage, but you can also have it in a decimal, and we'll talk about that in just a second. This equation could use the useful output power divided by the total input power, or it could all be in terms of energy, so the useful output energy divided by the total input energy. Either way, you have to make sure that you've either got a ratio of powers or a ratio of energy, because the efficiency has no units, okay? Really, really important. Now, if you just do this number divided by that number, you should get a decimal. That is always going to be less than 1 because no transfer is 100% efficient. If you take that decimal and you multiply it by 100% to get your answer in terms of a percentage, which is what we've done up here, 13%, 87%, etc., then you multiply it by 100% and you will get a percentage between 0 and 100%, but it should be less than 100% because, again, no energy transfer is 100% efficient. So let's have a little look at calculating the efficiency of the kettle. The energy transferred to the thermal store of the water was 184,800 joules. And the energy transferred by the electrical current in the kettle was 211,600 joules. So the useful output was the energy transferred to the thermal store of the water, and the total input was the energy transferred by the electrical current. So here is our equation, and you can see we're both in energy here, so we're going to get a ratio with no units, so that is great. When I do this calculation, I get an efficiency of 0.87. If I wanted to, I could multiply that 0.87 by 100%, and that would give me an efficiency of 87%. Either of these is acceptable. Just look carefully at the wording of the question to see how they want your answer. So we're now onto our final job for this video. So we've calculated work done, we've calculated power, we've calculated efficiency, and our final job to do was to look at ways of improving efficiency in energy transfers. And the way that I want you to remember this, or to sort of have an overview of this, is to think about these 3 different ways that we were doing work and transferring energy in the first place. We could do work via a force, mechanically. We could do work via a charge flowing in a circuit, or we could do work via heating. And if we look at making all of these transfers more efficient, then less energy is going to be wasted and dissipated to the surroundings as thermal heat energy. So if we start by looking at how we can improve the efficiency of a charge flowing in a circuit, what we're trying to do is to reduce the heating in the wires as the charge flows around the circuit. And if you've done your electricity topic, you'll remember that in the national grid, What do we do to improve the efficiency of the energy transfer on the national grid? We decrease the current and increase the voltage using those transformers. So if you wanted to increase the efficiency of a charge flowing around a circuit and transferring energy, decrease the current, because that will reduce energy wasted via heating. Next, we're going to look at improving the efficiency of the work done via heating. Okay, so if we want to make transfers of energy via heating more efficient, we need to use insulation. Okay, that is going to decrease the thermal conductivity of the materials involved, and so less energy will be dissipated to the surroundings, and it will all be put into the useful thermal store that we want it to be. Some examples apply to homes and houses. If you've got a house, we want the energy transferred to the useful thermal store of the house. We don't want it going outside to the surroundings. We need to make sure our home is insulated. We can have cavity wall insulation. We can have insulation in the roof. If our building has thicker walls, that's going to lower the thermal conductivity, and that will reduce wasted energy to the surroundings. If we put double glazing in, that will do the same. And if, let's say, for example, you've got a chimney or a fireplace in your house, if you have more of the chimney inside the home, then the energy can be transferred from the chimney into the home before it goes out into the surroundings. And then finally, if we're looking at energy transferred or work done via a force, we're trying to do two main things here. We're trying to reduce heating by friction, and we're going to use machines. Those two things will increase efficiency. So let's look at some more specific examples. If we're trying to reduce energy wasted by friction, we can move more slowly. We can make sure that vehicles are streamlined, and we can use lubricants to reduce friction. Now, in terms of using machines to make energy transfers via forces more efficient, we are, again, actually still looking at reducing friction, but we're going to do it by things like this. We're going to use wheels, okay? They're going to reduce friction, make things more efficient. We're going to use gears to transfer forces. We're going to use levers, and we're going to use pulleys. All of these things feature in most of the machines that we're using in everyday life to transfer energy mechanically via forces, and they're all based on this idea of reducing friction. If we reduce friction, we reduce the energy that's wasted and transferred to the surroundings. We reduce the energy that's dissipated. That improves the efficiency of the transfer. So this is our overview of different ways to improve the efficiency of energy transfers. So that is it in terms of what we were aiming to do. We were looking at calculating the work done mechanically by forces, by a current in an electrical circuit, and by heating. We've done those calculations. We looked at how to calculate power and how to calculate efficiency, and we looked at an example of a Sankey diagram, and we have looked at ways to improve efficiency. So this video with the previous video should give you a really good overview of energy stores, work, power and efficiency. It might be that you're using these videos to introduce these topics to you, or you might be using them as revision videos. Either way, make sure you're writing summary notes, that you bring any questions to the next lesson, and that you follow up these ideas with some practice questions. Well done, I will see you soon.